So my name is Kevin Tobias. I'm Director of Product Management at Kratos Space. And today I want to talk to you guys about the $35 billion question. How can satellite meet the telco need? So without further ado, let's get started. I'll give you a little agenda here. So we'll have an introduction about a background on space, what's happening in space. I'll give you a little introduction about Kratos. We'll talk about what's happening in space. It's a time of disruption, so I'll describe that, give some examples, and then the opportunity that satellite has to meet some of the telco needs from a growth perspective. And then I'll talk about how open standards can really lead the way to help satellite capture that opportunity. So intro-wise, you might be wondering why someone from Kratos Defense is here talking to you about telco. And so just a little bit about Kratos. Kratos has a number of divisions. I'm part of the Kratos Space Division, and we're about 50-50 defense and commercial. So 80% of commercial satellite and space operations rely on Kratos products today. About 90% of US DoD missions rely on Kratos Defense today. So we're very well proliferated. We've been in satellite for 30 years. I have a lot of experience in that realm. And really what we're going to be talking about today is more in the SATCOM realm, but we have a lot of experience traditionally in command and control of satellites, telemetry, so basically flying the satellites themselves, lots of missions, Earth observation, space domain awareness, and satellite communications. But specifically, let's talk about SATCOM. So connectivity is now expected. Everywhere we go, doesn't matter if you're on a plane, if you're on a cruise ship, if you're on an island, if you're out hiking, you're on the top of a mountain, everyone just expects that you're going to be connected all the time. And it's not enough now to just be able to make a phone call or have a text message. You've got to be able to upload a video, right? And we used to see that it was all about being able to download stuff, and now the tables have turned and we have to be able to uplink things back to the internet. So that's a baseline. Connectivity just expected everywhere you go. And the expectation is that it's seamless, right? You shouldn't know what you're actually connected to in terms of an access network. You're just connected to the internet. Another thing that's emerging is, you hear this phrase, data is the new oil. So if every sensor and everything that is out there generates data, and data is the fuel that we use for AI to develop value, to bring insights, to make things more efficient, then the next struggle is, if that's the case, how do I connect to all of the things that are collecting all of this data? And satellite has been around for quite a long time. Most people don't know. One of the first satellite communications with Telstar 1 was 1962, right? So we've been doing this for over 50 years. And the important part is when we think about data and connectivity and ubiquity, the only access technology that can get you there is satellite. And part of that is pretty easy. If you're 35,000 kilometers above the Earth in geosynchronous orbit, you only need 3 satellites to see the entire Earth, right? So just the vantage point there. Now that comes with disadvantages, of course. If you're 35,000 kilometers away, physics kind of gets in the way and says there's going to be latency in between, right? But satellite access has made a way to bring connectivity, to access sensors and bring back data. So, why has it not been enough? And so that's what we're going to talk about a little bit today. And so I gave you a little bit of a backdrop, so I'm just going to build this slide out to kind of give you a picture of the landscape. And so because of that insatiable demand for data, the satellite operators are responding by putting up more satellites. They're responding by putting up more bandwidth, so high throughput satellites. You can see some facts here about in the next decade, $270 billion opportunity for the satellite operators to go off and capture some of this revenue. You see the customers continuing to ask for more demand for data. And the way I always say it is, if you bring the pipe, it doesn't matter how much throughput you can bring, it will fill up almost immediately, no matter what the particular use case is. And then there's kind of this emergence on the telco side of the house. The most interesting fact you see on the screen there is that satellite while it is the only ubiquitous connection and connectivity, it only makes up about 1% market share for the telcos. So you have to ask yourself, well, why is that the case? And the answer is that satellite is very manual, it's very static, it's very proprietary, it's very complex. Each vendor and each system has its own proprietary waveforms and hardware. It's hard to deploy. It doesn't integrate well with terrestrial technologies. And so what I want to talk about a little bit today is if that technology solves at least the physics side of it, how can we solve the operational side of being able to capture that opportunity? And a little shameless plug from Kratos. One of the products that we're bringing to market at Kratos Space is called OpenSpace. And OpenSpace, as the name implies, really is an open standards-based cloud-native approach. So we're at SUSECON. OpenSpace is its foundation is cloud-native. So we're built on a SUSE stack from RKE2 on our gateway side to K3S lightweight Kubernetes, and using, if you've listened to any of the sessions on the Edge stack and Edge 3.0, very similar stack there. It's a far edge single node cluster that's out at the edge of a satellite network. And so what we're able to do here is by having a cloud native baseline, we're able to basically take the network functions that were traditionally proprietary, purpose-built hardware that did all of the complex digital signal processing and virtualize those things and run them as software. And so I'm going to talk to you a little bit about how that cloud native, that open standards-based environment kind of paves a way towards capturing some of the telco opportunity. And so just a kind of a quick overview of OpenSpace so you get a picture for what I just described. On the left and the right-hand side of the image here, you see what represents what we would call a gateway, which is just connected to the internet backbone and provides service out to the far edge locations. The far edge location is your plane. That's how you got in-flight connectivity when you were on the way here. That was connected with satellite. Your hard to reach places, so oil rigs, cruise ships, and then quite frankly, just places where terrestrial connectivity, the business case wouldn't close for that last mile to run fiber to bring another cell tower out there. That's where satellite kind of comes into the mix. And each one of these blocks you hear represent essentially a containerized network function that takes care of the channelizing, combining, modulation. These are the various network function steps that it takes to go from an analog signal, process it, and out comes internet traffic or IP traffic on the other side. And so for us, we come down analog from the satellite. It's an electromagnetic wave propagated up to a satellite in various different orbits. And we convert that to digital through something we call a digitizer. And we have a standard packet. The satellite industry, we're talking about standards now, has come around to standardize this conversion or digitizing to a standard called Diffie. And it's governed by IEEE, just like Wi-Fi and Ethernet. You expect with Ethernet and Wi-Fi, you just plug things in and they just work. That's exactly what this is for the satellite industry. And it allows those network functions to be represented in software. And so when we think about actually fulfilling a service, instead of having to send a person, an installer, a network operator, an IT guy to sit there and stack up all of the network functions, configure them with actual physical Ethernet cables, all of these steps move away towards a virtual environment where we can string together containerized network functions in what we call service chains. And so this is really going to revolutionize the way that satellite networks are deployed. And some of the benefits we're going to talk about here are as we move towards standardizing more of satellite, like the waveform, like APIs, this starts to give us a future-proof path towards being able to provide solutions that the telco operators can use. So let's talk about the opportunity and disruption that's happening at the space layer. So this slide changes every single time I present it because there's so many things that are happening in space right now. On the top right-hand side, you see a variety of different satellite vendors that are creating software-defined satellites. The key here is satellites were static, and they used to go up for a 15-year mission, and they would have capacity over a particular area for its whole lifespan of 15 years. So if the business plan changes 2 years into it, well, you're kind of out of luck. Once you move software defined, that means that you can now change the configuration of the satellite, all of the different parameters of power and bandwidth, and you can steer that capacity over a region. So it could be a conflict, it could be a natural disaster, it could just be a new business that you want to put up. Now you can move from 15 years life cycle down to change it every 15 minutes. That's the promise of software-defined satellites. These are going up. Over 60% of satellites that are on order today are software-defined. So this is the future, there's no doubt about it. And then the disruption that even if you're not folks that are very familiar with space or satellite, most people have heard of Starlink. And Starlink is really disrupting the satellite industry by bringing what's called an NGSO constellation, or a low Earth orbit constellation. I talked about ones that were at 35,000 kilometers. These are all the way down at 1,000 kilometers. So the problem with latency of having 500, 600, 700 milliseconds of latency from a GEO comes down to under 100 milliseconds. The latest things I've seen have been around 20 milliseconds. It starts to sound like fiber, and in many cases even faster than going through ground infrastructure. So it's a really big change in disruption. So as a response to that, you see all these pluses here. These are operators that have been around, many of them for decades, and have been major players in the satellite industry, all merging together. They're all merging together because there's disruption that's happening. And then on the left-hand side, the opportunity on the telco side is growing exponentially, where the insatiable, ubiquitous demand that comes in the world that we live in today is a growing opportunity for the satellite operators. And so what's happening on the telco side is an alignment with standards. And so we're going to talk about a few of those through the rest of these slides. And a few of those are 3GPP. So any of you with a cell phone, you've been using 4G and 5G, that standard is been ratified by the 3GPP body, and 5G for the first time has included something called NTN. The most recent release 17, has this NTN thing, and it's a nice way of saying standard satellite. It's just satellite. And the idea is the telcos want to be able to say, I have demand here, 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 and I want to be able to deploy it the exact same way that I deploy the UE that's in your pocket, and be able to deploy it in a common way instead of this complex way that networks are rolled out today. And then on the top side of this happened. We're all here at SUSECON, and we're talking about virtualization, and network function virtualization happened over a decade ago, and the telcos recognized that they needed to disaggregate the network functions from the proprietary hardware and be able to instantiate networks in a software-defined way. So the standard that I talked to you about called Diffie is making that possible by digitizing and then enabling basically digital signal processing in cloud-native environments. So it's this really big picture of what's going on, and then you see the response. So this huge demand, right, for the data, and we're going to see 10x the number of satellites from the beginning of this decade to the end of this decade. And this is from GSMA, NSR, and a few other analysts have been basically characterizing what that growth looks like, and this isn't very hard to characterize. These are things that are already on order and have launch plans. So this could grow even more from that. And the telco demand that's growing, they're looking at a number of different use cases. One of those use cases is consumer. So you may have heard of direct-to-device. So Apple was one of the first from a cell phone perspective to say, hey, we're going to invest in a satellite constellation so that your phone can talk directly to a satellite. And typically satellite phones in the past, they had a big old omnidirectional kind of antenna on it. They were very bulky and expensive. But the whole goal was to have standards, to have non-terrestrial standards that allowed these devices. At this point in time, they can send out an SOS message. They can send a text message. The enhancements that are coming for direct-to-device will include being able to make phone calls. So for a telco, being able to say, well, this is the edge of my cell range with my tower, be able to have that user be able to switch to satellite and not know the difference. So they have coverage all the time. It's through a variety of different access technologies. So that's one of the first ones, called the direct-to-device. But that's a little bit limited. So the standard talks a lot about lower frequency ranges, much smaller carrier sizes, which just equates to lower bandwidth. So it's fine for sensors, for making phone calls and text messages. But the next wave is really, a lot of that stuff would be considered IoT, Now we're really moving into what's called new radio with 5G, and they have provision for this end-to-end aspect to it so that they can bring the new radio standard to basically all of the other things that I talked about that satellite can reach today. So you're starting to see this terrestrial and non-terrestrial technologies begin to converge, but there's some missing pieces in making that seamless, which is really the opportunity that's here to capture the telco revenue opportunity and really help them capture and provide the connectivity to their customers. So what does that opportunity look like from a revenue perspective? It's quite massive. So in the trillions of dollars that the telcos go after, if you look at the revenues of telcos, they're talking $100 to $150 billion a year. This is an opportunity for satellite alone within that opportunity. And it's broken down here by consumer. And so consumer is mostly direct to device, like I talked about. And so you'll see enhancements in that. And then the B2B or enterprise and government are going to cover those other use cases I talked about, like enterprise branch offices. You can think about industrial IoT. Again, all of the mobility use cases where once you leave terrestrial range, you're out of luck unless you have satellite. So quite the massive opportunity that continues to grow year over year. And so what and how can we answer this call within the satellite industry? And it's pretty clear that open standards lead the way to make this happen. And so I talked about 5G NTN. I talked about Diffie. And these are things at the network layer that will essentially pave the way for there to be a standard network that converges both non-terrestrial and terrestrial networks. It also paves the way for network function virtualization, being able to run these in a disaggregated way, the way that 5G is moving along. It's the same story if you've watched 5G and you've watched Nokia and you've watched Ericsson and you've watched these vendors have to move away from their proprietary hardware. The exact same thing is happening in space, and this kind of allows the two to come together. Then the ultimate goal is that a satellite operator might be able to use common service calls to be able to instantiate a new service, right? And this doesn't just go for the telcos. It goes for mission critical. Think first responders. Think in conflict. When something arises, whether it's a business need or it's something mission critical or you need to change the mission directive, being able to have a set of service calls that you can make that deploy that service in a matter of minutes is a game changer. Because today, if you want to go and do that, you're sending a person to go stack up the equipment. And so there's lots of logistics that are involved in actually sending people to the end sites. There's a lot of logistics involved in knowing what to configure. So those kind of really pave the way. So MEF is Metro Ethernet Forum. And then TM Forum, which actually has an event, I think it's called Ignite, is going on this week. And this is actually one of the topics. And they're talking about how they can actually go and instantiate these calls using MEF LSO as an example, and that's lifecycle service orchestration. And these are standards that the telcos are already using. So we're just bringing these into the non-terrestrial and satellite world. So as an illustration here of 5G NTNs, because I've gave you a lot of words and I talked through some of the use cases and I talked about how it starts to answer the call. These are some kind of higher level drawings to give you an idea of some of the network functions that are required to go off and deploy these things. And the direct to device one that you see up top is in existence today. You see it on the Apple phones. Android is next. They're working with companies like Iridium, and basically these are all NTN technologies that are enabling, again, today just SOS and text messages, but you'll see this. Each release, there's going to be more and more. I think Apple just announced that they're going to allow regular text messages. So you're going to continue to see these enhancements. And in that case, really the satellite is just acting like a relay, and you have your traditional G node B, which is usually at the base of a cell tower, in this case is at the gateway, and they're just using basically the satellite transparently. As we move into new radio, that's what NR stands for there, and NTN specifically, you'll start to see some regenerative use cases where basically we take some of the network functions, and again, this is why it's important that they've been virtualized, is now if each point of presence and edge has compute, and that's not just at the gateway side at the near edge or the far edge, it's also on the spacecraft. So once we have that on the spacecraft, it means that even if we put the spacecraft up and we didn't have this use case in mind, if it's there, it means we can now, in a software way, go and deploy this network function. So what's happening in 5G is they can split up network functions. Here, you might even want to run part of the G-Node B up on the satellite, and what that will do is it will provide a shorter link instead of needing to go all the way back down to the ground. It will provide a shorter link with lower latency. So you're starting to see all of these different use cases kind of proliferate and answer the call for the telcos for them to be able to capture this opportunity. And then network function virtualization and software-defined networks really are the tenets that allow these networks to be future-proofed. One thing that has plagued the satellite industry is when you go to deploy something out in a very remote location, again, we're going there because this is the only way to get connectivity, you have to make a very good guess, because if it's an oil rig, you're sending a helicopter. And if you're sending a helicopter, that's way more expensive than any of the equipment that you're putting out there. And so you have to count that into your business case before you can get a return on investment. All of the costs that I have for the equipment and having to install it can be very high. So they don't want to ever go back. You know, in telco, we called it the truck roll. In satellite, we call it the helicopter ride. You don't want to go back. And so how do we prevent going back? Well, in the past, it was either underinvest or overinvest. Underinvest meaning, well, I'm just going to put the bare minimum out there, and if the business case grows, then I guess I'm just going to have to go back. Or overinvest thinking it's going to be really big, and then it never happens, right? And so you've spent all this money that you can't actually utilize. Once we're software defined, we can provision general purpose compute from a variety of different ecosystem vendors, and we can deploy what we need when we need it, right? So it's a complete game changer for the satellite industry. It sounds quite obvious, but it's taken the satellite industry a while to come around to this, and the standards along with this digital transformation are really paving the way for this to actually become a reality. So some technical features here, but basically just putting this into practice, how we think this looks from a topology perspective, it goes back to what I already showed we're deploying with OpenSpace, with other waveforms, and as this 5G NTN standard is ratified and continues to move forward, we have a topology and a path that our operators can move towards this new waveform by simply doing a software upgrade. So again, that's why it's so important to be virtualized, to be cloud native as a tenet for this transformation. This is a use case to give you an example. And I'll start with the use case on the bottom of the diagram. And so this is just a traditional 5G core. They exist all over the place today. And you've got a base station, which all of us are probably connected to at the moment. And traditionally, there's a G-Node B that's down at the base station of the cell tower. Could even be a small cell. It's a variety of different topologies. And those connect to your end device, your UE. So the top part of the diagram represents the areas where we were not able to run fiber because maybe the use case didn't make sense, or maybe because it's 30,000 feet in the air or it's in the ocean, whatever the case may be. We simply are finding a satellite that has basically coverage and capacity over that particular region, and we're putting our G-Node B at the base of that gateway antenna, and then we're putting an open edge terminal, which actually has the modem on that virtualized, and then can also host the G-Node B in certain use cases so that we can put a cell tower up there. So basically what it means is now instead of having a fiber backbone coming in, I can drop a cell tower anywhere I want, and my 5G core will see that just the same as any other cell tower that I have out there. So it's a very quick way to say, if I have a use case where I want to get 5G connectivity, I can simply drop a terminal in an NTN configuration and have 5G connection. And by the way, this can be mobile. So one thing that you'll see probably soon is you'll start to roam onto the aircraft. Instead of going through the really obnoxious Wi-Fi and having to log in and all those things, they'll be roaming, there'll be 5G small cells or picocells on the plane, and you will seamlessly roam onto the plane, and all of the operators will work together. There's something called the Seamless Air Alliance. This is something that's actually in motion. But it starts to give you a picture for the ubiquity of 5G, and you get to a place where you don't even know what you're connected to anymore. At the end of the day, this is what the telcos want to get to. So this use case here is quite interesting because I showed you that picture of all of the different spacecraft that are going up, tens of thousands of spacecraft going up over the next decade in LEO and MEO and GEO, and all of them have their various uses and coverage and throughputs and latency. And so depending on your use case, if you have IoT, you don't really care about latency because it's very bursty, it's very low data rate. But if you're talking about mission critical ISR, you're talking about video feeds, well, then you want the lowest latency possible. You're talking about trading, you want the lowest latency possible. And so by having these multiple operators that the telcos can work with, they can make a MEF call for a service, and based on that quality of service that's needed for the particular use case, it can go pick whatever network makes the most sense. And this is just showing a variety of those networks. Or in the case where you're roaming across multiple areas, that's why in some cases you have multiple SIM cards in like maritime use cases to be able to roam across users. You'll be able to do this, but from a satellite perspective. So that you really begin to get this seamless ubiquity, and this is really the value that the telcos are looking to bring to the end customers. And 5G NTN, cloud native, virtualization, a lot of the APIs that I've showed with MEF are really the way to make that transformation happen. This is just a quick example before I wrap up. So I've got about 3 minutes here. Is an example of Open Satcom management, and you can see this is part of last year's TM forum presentation Kratos participated in, and this really showed a way that we could, if you looked at the last use case where we had multiple different orbits, potentially from multiple different operators, a common set of calls can be made, and this results in the services being able to be provisioned and activated in a common way for the telcos or seamlessly. And that's one of the big things is today, each one of the access technologies in satellite are very proprietary and clunky. So having one way to do it, being able to submit one call from a variety of different operators really starts to fulfill the need. And then this provides a standard reference architecture for enabling that end-to-end orchestration needed across the operators. So to summarize, data and connectivity demand obviously at an all-time high. I don't think that's controversial. Everybody can get down with that one. Ubiquitous demand for data requires satellite access. Again, that's pretty clear. That's going to continue to be the case. So the opportunity for satellite to play a pivotal role in the telco operations is here and now, and it's bigger than ever. So this is something we're really excited about. And our belief is that open standards and digital transformation will make it possible to capture that opportunity. So with that, I thank you for your time and appreciate you attending the seminar.